All right. So let's, did I start class for you to log in? Yes, I did. Okay. That's not something we need. All right, let's go ahead and, um, so oh, that's a good group. I've already picked out some that I want to work on here. So let's start with number 25. Actually, we can start with number 14. It doesn't, I guess, matter what order we go in here. But if we look at, there's a comment I wanted to make about number 14. Number 14 said to look back at this picture right here. And you were supposed to estimate f prime at 0. Is that correct? Okay, I think I've got my numbers right, but if I'm not, now at any point along the way, so a lot of this today is going to be me saying, okay, I'm going to go over this problem, I'm going to go over this problem, I'm going to go over this problem. Now at any point, if you've got a question, if you're unsure of something I'm saying, if you have something a little different, you want to know if that's correct, please, interrupt me, raise your hand, whatever, and let's talk about it. But a lot of the time, I'm just going to be rolling along here talking about some of the things I really think are important. But if something comes up that you're a little confused by or whatever, please stop me and let's talk about it, okay? So we're supposed to find f prime of 0. Now what they intended for you to do, and you probably, if you looked back on that page, you notice that earlier classes have already drawn in your book. Did you notice that? And I encouraged them to do that. And if you've got, one of the newer ones, although they're not that new, you may not have it, but so one way to find f prime, which means slope, we want the slope at 0. One way to do that is to draw the tangent line, actually draw it in there. And it's not very good, but really this graph is pretty straight right through this region. So the curve itself is almost like the tangent line. But when I do these, I like to really extend them quite a ways. And the reason for that, and this is something you'll have to do on our next quiz, I'm almost guarantee you there will be a graph without an equation on it, and I will ask you to estimate f prime at some point. And what I'm wanting you to do is go in there and do this. Sketch a tangent line and do a slope triangle. Over 1, in this case it looks like it goes down, I don't know, about 6 maybe, a little past 5. So this would be maybe around -6. I think that's a good, reasonable answer for number 14. Now notice, because the units are different on the y, the units are 5, right? Now, somebody might have -5, somebody might have -7, whatever, and I understand that. So if this was a quiz and I was grading this, I would be looking at your picture. I want to see the tangent line. I want to see the rise and the run in there. Some of you are better at showing your work than others, okay? On a problem like this, where you need to do the slope of the tangent line, I'm going to be looking for that. So if you have -7, I want to know where that -7 came from. And if it's, if your line is not a very good line, you might lose some points for that. I mean, you want to draw, you need to be able to at least draw as good as I can. That's not very hard, okay? So -5, -6, -7, somewhere in that ballpark, you got a decent picture, that'll be good. All right, so that's the first one I wanted to look at and talk about. So let's go on to number 25, the speed limit law. Now, here's the information on number 25. Now, they're asking if this is a true statement, or they're saying you should show that this is true. Well, let's talk about this. So what does this say to you when you see h of 0 equals 0? That's a point on the h graph. So I'm over here going to draw the h graph, and it's very important, like I was saying earlier, to label. If you're going to draw graphs of something, very important to label it, okay? Because we have different graphs we talk about. We talk about the h graph. We also might want to talk about the h prime graph. Now, not in this problem necessarily, but let's label this the h graph. So that tells us we have this point right here. It's like a starting point. This tells us what? Slope. There we go. That's the key word. When you read this, the first thing that ought to come to mind is either slope or rate of change. In this problem, slope is probably the more useful term. So the slope is never greater than -2, or always less than or equal to -2. Now here's where and Kelsey and I, we were having this conversation here just a few minutes ago about this. When we're talking about slopes, and also when we're talking about velocities, we got to be careful, because if I tell you that my velocity is decreasing, what's the first thing you thought of? Pretend you're in a car where the velocity is decreasing. What do you imagine is happening? Slowing down. We would all think that, but that's not right. That's not true. Now again, if you're in physics, you understand this a little bit more maybe, because what does velocity include? Direction. Velocity includes direction. So if your velocity is decreasing, there are two possible ways your velocity is decreasing. Let's talk about this. If I'm east of Bismarck, and I'm going to the right, my velocity is positive, right? So let's say I'm going 50 miles an hour. One way my velocity can decrease is be 50, then 40, then 30, then 20, right? That's a decrease. Am I slowing down? Yes, right? 50, 40, 30, that's slowing down. But I could be going west. If I'm going west at 50 miles an hour, what's my velocity? -50. If I go -50, then -40, then -30, am I slowing down? I tricked you. You didn't think I was going to say it. Am I slowing down? Yes. So if I'm going -50, -40, -30, I'm slowing down. What are those numbers doing? Increasing. -50, -40, -30 is an increasing number, but I'm slowing down, right? So we've got to be careful. The same thing with slope. If the slopes are increasing, does that mean they're getting steeper? It could. It's the same thing. If the slopes are increasing, are they getting steeper? Well, let's look at it. If the slope is 3, then 4, then 5, then 6, are those slopes getting steeper? Yes. But if the slope is -3, -2, -1, are those getting steeper? -3 slope would be like this. -2 slope would be like this. -1 slope would be like this. They're not getting steeper. But what are those numbers doing? Increasing. So just because the slopes are increasing does not mean the line's getting steeper. We have to be careful with our positive and our negative numbers. So the term increasing and decreasing can sometimes get us in trouble. So what I like to say to help with that is I like to say negative and getting more negative. To me, that's -3, -4, -5, -6. Or negative and getting less negative. To me, that's helpful, because now if it's negative and getting less negative, now it's getting less steep or it's slowing down. Does that make sense? All right, so back to this. So the slope has to be less than -2. So that would be numbers like -2, -3, -4. So what's that mean for slope? Steeper. -2, -3, -4 means it's getting steeper. Okay, so it could be -2 slope, but it could also be it could be steeper than that. All right, so now here we go to this. So now they want us to say h of 5. Well, that means if you go over 5, so let's think slope. What happens if I go over 5 and my slope has to be at least this steep? If you go over 5 and you have a -2 slope, where are you going? You've got to go down at least to -10 right here. But maybe if the slope is more steep, it could go where? Farther down. So h of 5 doesn't, so isn't it true that h of 5 has to be less than -10? Yes. Now, this was a quiz and you were supposed to show this. I think what you need is that picture and those words that I was just saying. It might sound something like this. If you start at 0, 0, and you go over to the right 5, if the slope is -2, you would have to go down at least 10. But since the slope could be -3, 0.4. It could go down even more. Some words like that, written out in conjunction with that graph, to me is how you explain it. Okay? I think it's really hard without some words, and I think it's really hard without the graph to fully answer that question. So, if that was worth 2 or 3 points for the explanation, you know, you better have all that stuff if you want the full points there. All right. And then they ask this. Now, this gets confusing. You got to think about it. True or false? This was in the back of the book, so maybe you looked right. True or false? It is true. Now, what threw some people off on this one is you do the same reasoning. You say, well, if I go over 3 and the slope's -2, I got to go down what? At least 6. But I could go down even more. So this one, h of 3 has to be less than or equal to -6. Well, is that less than 5? Absolutely. All of these points down here are less than or equal to less than or equal to 5. Now, some people say, but wait a minute, it says equal to, so it could be equal to 5. Well, but it's an or. It'd be one or the other, right? So it's kind of like if I say I have less than or equal to $1 million in my pocket, right? It's not it doesn't tell you much about what I have in my pocket, but it's definitely true, right? I don't have $1 million, but I don't have to have it. If I have less than or equal to, then it's a true statement. So all these numbers down here are less than or equal to 5. Okay? They're all less than. None of them are equal, but it doesn't matter. The equal can still be on it. Okay? So that is a true statement. All right, let's talk about C, card talk. So what we're talking about with this is we're going back to here. Instead of the black part where we talk about slope, let's talk about time and speed and distance we traveled. So let's put in miles per hour in this. So what you would do on this one, and like Kelsey had it right, it would be like a paragraph of writing probably to really fully say this. That wouldn't be that long, a couple sentences maybe. But this would tell you what? In car language. Starting point. In 0 time, you're at 0. So that's Bismarck. Let's call that 0 right here. That's Bismarck. We'll use east and west again today. Okay? So we're going to start it at point 0. Call it Bismarck. What's this tell you? Going west. 2 miles an hour, could be going faster, right? 3, 4, but we're going at least 2 miles an hour and we're going west. So h of 5 then would be what? Well, but forget that. H of 5 would just reference what? At 5 hours, how many miles, right? H prime is miles per hour, H is miles. So at 5 hours, how many miles? Where am I at? What's my position in miles? Less than or equal to -10. Now we got to think about less than. Where's -10 in miles in this scenario? It's west, 10 miles. What's less than 10 miles west? Wouldn't it be 11 or 12? Because that'd be -10, -11, -12. Those are less than numbers. So more west is actually less than. More west is less than. Which makes sense. A number line farther left is less than. So this is saying then, start at Bismarck. We're going to go 2 miles an hour or faster to the west. So 5 hours later, we have to be at least 10 miles west. That's what that would say in car time. And it makes sense. If you're going 2 miles an hour, you go for 5 hours, you got to be at least 10 miles west. This is the fun one. This is saying after 3 hours of going 2 miles an hour to the west, you are, what's less than mean? Further west. You are further west than 5 miles east, are we? For sure. We're 6 miles west, so we're definitely further west than 5 miles east. Tricky. Okay? But it's cool how we can put that into slope language, graphical language, or we can put the same thing into this rate and rate of change kind of language, and it means the same thing. All right. Number 28 then would be just, let's do this, because now that you've done that and let it soak in a little bit, let's see if we can do it on a fresh problem. So we would start with a graph. It's the F graph. What are we going to do with f of 0 equals 2? Plot it. This tells us the slope is steeper than 4 or steeper, 4, 5, 6, 7, those kind of numbers. And we want to know about f of 1. So if I go over 1, so to me this is the picture. If I go over 1, I have to go at least 4 up. Well, if I go 4 up from here, that puts me at 6. It has to go at least that high. It could go higher. So f of 1 has to be greater than or equal to 6. That's what they were wanting you to say. And then the same thing. Okay? There will be a problem, speed limit law like 25 or 28 on our next quiz. Okay? The key is drawing it as slope, drawing and plotting these points. This means slope. This is a point. These are points on the f-graph. Rise over run. It's really just rise over run. It's all it is. And again, the two key numbers to think of are here and here. Those inputs. Because what that's telling you, that's your run. Right? That's telling you you're starting at 0 and you're going to go over 1. Or like in the last problem, we started at 0 and going over 5. And then the rest of it you get from the slope there. But if you know the run and you know the slope, you know what the rise is supposed to be. And that's really the gist of speed limit law problem. All right, let's talk about this section right here. We did record, right? Yeah, okay. So let's talk about these problems. Position, velocity, acceleration. Now, what's another name for velocity in this situation? P prime. Now, what's another name for acceleration? V prime, but also, no, P double prime, right? P is the original function. The derivative of P is the velocity. And the derivative of velocity is acceleration. So derivative of velocity means V prime, but that's also the second derivative. That's also the derivative of P prime, which makes it P double prime. Okay? So understand that notation. Position, velocity, acceleration. That is a very common grouping we'll use a lot for derivatives. All right, the first problem says you're moving away from the origin at a constant rate. That would look like this. Okay? It's a line. Now, say it again. I said it yesterday. I can't say it enough. The derivative graph is a plotting of the y values of the slope of the original function. So on this graph, we need to plot the slope of this graph. Well, what is the slope of this graph? 1, 2, I don't know, but it's definitely positive. And it's constant. It's the same slope all the time. So if this is a slope of 1 here, it's a slope of 1 here, it's a slope of 1 there, it's a slope of 1 there. That means what has to be true over here? The y values have to all be 1, right? This graph, y values are the slopes of that graph. So that's got to be a horizontal line up here at 1. Not on the x-axis. Can't be on the x-axis. What's the graph here? On the x-axis, because the slope of this line is 0. Slope of 0, slope of 0, slope of 0, slope of 0. So over here we would be graphing y values of 0. And we would have a horizontal line. So that would be 0 acceleration, constant speed, 0 acceleration. Okay, look this time. We go home. No. Class is ended. All right, there it is. All right, now 35. 35 says that the object moves to the right and then to the left. Now, there's two options you could have done here. One option would have been this. How many people drew their graph like that for 35? A few. Okay. That's fine. Now, physically, that's kind of impossible, right? Because what that would mean is that it's going at a constant speed, doesn't even stop. Well, it instantly switches direction going at that same constant speed. which, like I said, physically would be kind of hard to do. Now, that does bring up something we're going to talk about today when you get to a sharp point like this. Okay? So we'll kind of visit that right now. So how would we graph this over here? And this is a part I'm guessing many of you didn't get. You may have done this, but you may not have gotten this part right. Remember, well, what are these slopes right here? Positive and, well, heck, it's the same thing we just did up here. You guys said that was horizontal, so this has got to be horizontal right here. Because this slope is 1, 1, 1, 1, 1, 1. These y values got to be 1, 1, 1, 1. But then they instantly change to what? -1. That means they instantly come down and do this. Piecewise. There you go. Now the real question is, what is the slope right here? Well, you would think the two choices really would be it's either 0 or it's undefined. Turns out, and this is one of the new things, we'll just throw it out there now, it's undefined. Whenever you have it, we'll put that in our notes later, but whenever you have a sharp point like that on the graph, the slope does not exist at that point. It is undefined. So technically what we would have here would be an open circle here and here. Now, if you drew a position graph like this, this would have to be your velocity graph. Then what would your acceleration be? Well, it'd be these slopes. What are these slopes? 0. Except right there, there'd be nothing. So there'd be like a hole there. So you'd have 0, a hole there, then 0. Okay? All right, 37. Well, oh, wait a minute. Let's do this in red. A more likely scenario would be a hill kind of a situation. For moves to the right, then moves to the left. Because then that allows for stopping and so forth. Now, if that was your graph for position, what would this graph look like? Well, let's talk about slope. What's the slope right back here? Let's think of a tangent line. What's that slope right there? Let's say it's bigger now. Let's say it's 4. It's pretty steep here at the beginning. Then what's the slope here? 3, 2, 1, 0. So what that means is if we're going to graph over here, we've got to plot those slopes. So if we started with a slope of 4, we got to go up here to 4. And then it was a slope of 3. And then it was a slope of 2. And then it was a slope of 1. And then it was a slope of 0. And then what is it after that? -1, -2, -3. So -1, -2, -3. And so what we would get is a line going down like that. So if you did the red graph as your position graph, then you need that red graph as your velocity graph. And then what would be the acceleration graph? Negative constant. Because this line would have a slope of, say, -1 the whole time. So these y values over here would have to be -1 the whole time. But it's really easy if all you think of is slope. If you just think, go along that red graph and think, what's this slope here? What's this slope here? What's this slope here? What's this slope here? And then just plot that over here as a y value. That's it. That's all you got to do. All right, 37 said it moved to, what did it say? Towards the origin at a steadily increasing rate. That's the key. So that means it has to go down like so. Now, it didn't say it had to start in the positive. It could have started below and come up. So we could have either been to the east and moved back to the west, or we could have been the west, moved back to the east. But it's got to be curving down like this. Concave down. So what would this graph look like? Here and go where? Like that. Again, think about the slopes. The slopes look like they start about 0, -1, -2, -3, -4, getting steeper. And so therefore this has got to go 0, -1, -2, -3, -4, the y value. And then the graph of this has a negative slope that's constant, so we would need to draw a negative horizontal line for a constant. All right. So these are all just different relationships about f prime graphs. Most of our emphasis here is graphical, okay? And that's the way we learn these things early in this book. We look at them graphical, which I think is good. It's a visual way of looking at these things. All right, let's talk about 41. 41. H is the hours between sunrise and sunset T days after January 1st. Somebody, I know this wasn't in the back of the book, so somebody want to take a crack at this one? Yeah. Yes. The question was, interpret this top line. Go. Perfect. Perfect. On day 100, the hours between sunrise and sunset, and the key was, this is what the other class, somebody in the other class didn't get, and they were near perfect, right? If I was picky on one word. Somebody in the other class said, on day 100, the number of hours between sunrise and sunset changes 0.05 hours per day. What was better about her answer? Increases. And why did she say increase? Because it's positive, right? If 0.05 was negative, we'd say decreases, okay? So change is good. Rate of change is what derivative's about, okay? But if it's positive, it's an increase, and if it's negative, it's a decrease. So that's perfect. Now, we could shorten that a little bit. Hours between sunrise and sunset, another way to talk about that is daylight hours, right? Daylight hours. Think about it right now. The days are getting what? Shorter. The days are getting shorter. The amount of, I mean, the days really aren't. They're still 24 hours. But daylight, right? That's what we say. The days are getting shorter. Less daylight at this time of year. I think this is a really interesting problem from a calculus perspective. So indulge me here a little bit while I go into this problem in a little more detail. On day 100, now I don't know what that is, a little more than 3 months, January, February, March, end of March, what? April something probably. April 1st, somewhere right around in there probably. All right, now, so it's increasing. Now 0.05 would be what, 12 minutes, I think? 0.05 times 60 would be 12 minutes, so about 12 minutes per day. Now another way that this is sometimes said is because, and the hours per day was really important there too. Another way this is sometimes said is the 100th day had 12 more minutes of daylight than the 99th day. Because that gets in that hour per day thing. And, really? Yeah. Well, I'm just trusting the other class. The other class had 12 minutes, and I went with it. Nobody corrected us. So it's isn't it 0.05 times 60? Oh, yeah. Where did I get that? Okay. Well, I didn't get it. It was the person in the other class. Okay, the other person in the other class was wrong on 2 counts. All right. They said changes, and they had to. So 3 minutes. I thought that was quite a bit. 12 minutes is quite a bit. But anyway, so that means the 100th day there were 3 more minutes of daylight than the day before. Okay, and you can see that when the days are getting longer, because after what's the day when the days start getting longer? December 21st. That's the winter solstice, right? The winter solstice. So after December 21st, the days start getting longer. So all the way until the summer solstice on June 21st, roughly, is when the days are getting longer. So there would be positive. So that kind of answers this question, right? When is H prime negative? Be from June 21st to December 21st, whatever those days are. I think in the book it said 174 to something or whatever. I wouldn't expect you to go through and be able to count exactly those days. Whatever, but that's when it would be. It would be, that's when the days are getting shorter. The hours of daylight's decreasing. All right, now, I want to look at a couple of things. I just want to investigate this problem a little further because I think there's some cool calculus kind of concepts in this. If we go back and we say this is December 21st right here, the winter solstice, that's when there's the fewest hours of daylight. Let's say there's 10 hours of daylight on that day, roughly. And then we go a full year, we'd be back to there. So let's say the largest number of daylight hours is on June 21st. Okay, let's say that's 15 hours of daylight. So wouldn't you expect this to kind of have a sine curve look to it? And in reality it does. Okay? And if you plotted that then over the years, it would just kind of, that's what it would be. Okay? Now, what do you suppose is those dates right there? Those are the inflection points. What days of the year are those? March, what's that called? Spring equinox. And this would be September. Did I get those backwards? I got those backwards. This would be March 21st, and this would be September, roughly September 21st, which is the spring and fall equinox. Now, why are they called equinox? Where's that name come from? Equal hours of daylight and nighttime, right? There's exactly 12 and 12, okay, on those days, and that's why they're called equinox. These are called the summer and winter solstice. What does that word mean? Sol is sun. This means, this comes from when the sun stands still. When the sun stands still. Now think about slope. What's the slope right here? Right? And when we talk about the car moving, when the car gets out to here and then turns around, what's the car have to do first? Slows down and then has to stop before it goes again. So this is like the sun stops. Now what does that mean the sun stops? We don't imagine the sun really stopping. It's not even moving, right? We're revolving around the sun. But the point being, but so what does this mean about the sun stopping? Well, I've drawn another little picture over here. I want you to imagine this. You're looking in the eastern sky. You guys are all facing east, right? We're facing east. So you watch the sunrise in the morning. Now, if I'm facing right straight east here, when the sun comes up, is it right in front of me? Is it over here to the north a little bit, or over here to the south? On any day, actually. It's to the south. Why? Because we're in the northern hemisphere. So the sun is a little bit in the southern sky. When it comes up, so it's coming up, so as we watch the sun, if we would track the sun, okay, maybe we said at noon let's do noon, let's say we did 10 a.m. every day. We tracked where the sun was up in the sky. So we're looking and we see it here. Now, in June, it's going to be pretty hot. In December, it's pretty low over here, right? And so right now, once the sun come across, it's pretty low in the sky. So I want to draw that right here. I want to draw that movement of the sun. So if we track that, if we started on June 21st at 10 a.m., we may see the sun right up there. Pretty hot. But every day it's moving a little bit this way, right? And by December 21st, it's, I don't know, it might be exaggerated, but it's farther down in the southern sky, correct? So what's happening? So from June, the sun is like moving, and by December 21st it's here, and then what happens? It goes back the other direction, right? So this is like where it gets its name. It's where the sun stands still. The sun is moving towards the southern sky. It stops, and then it starts coming back here to the northern sky, or farther towards the north, until June 21st it goes back. And not only that, but at the inflection point, which happens right in here, it's moving the fastest. The fastest. And think about that. Think about the days of the year. When you get to the longest day of the year, June 21st, the days seem pretty long, 9 o'clock, sun goes down 9:15, whatever. On June 22nd, June 23rd, June 24th, still seems about the same length, doesn't it? Through July, the days all seem pretty long. Then you start coming back to school in August, and all of a sudden you start noticing it, don't you? The days start getting shorter, and they start getting shorter pretty fast, right? That sun, every day the sun seems to go down a little more and quite a bit earlier. That's because we're getting towards September 21st, which is when those days are getting shorter the fastest. We said 3 minutes per day. Well, at some point in there, it's probably going more like, maybe 4 minutes per day or whatever. All right, but then as we get towards December here, pretty soon into November, into December, it slows down. And it's getting to this part of the graph, right, where it's going pretty slow, and all the days seem short. all the way through January, whatever. Okay, I think that's a really cool example because it shows this idea of inflection points and local max and mins, and it brings in derivative and this idea of increasing, decreasing, all that stuff. Pretty cool. Just nod your head, yes. Okay. All right, number 41. Almost done here. Number 41. Not, that was number 41. 47. 7 kind of looks like a 1. All right. You have this graph right here. What graph was this? This is a graph of f prime. Now, you might be saying, this was a really easy problem. Why are we doing this? Well, it is a very fundamental, basic problem that we need to be able to do, so I really want to emphasize it. The problem said, write the equation of the tangent line. Next quiz, guaranteed, you are going to have to do some, with given information, write an equation of the tangent line. Right? Now, we can't look at the tangent line because we don't have the f graph. They want the tangent line to some f graph. But we know the slope. That's what I mean. What do we need to write the equation line? Well, we need y equals the slope, x minus the x point, plus the y point. That's what we need. Now, they told us f of 1 is 5. What's that give us? That gives us that and that. That's beautiful. All we need is the slope. Now, we used to write m when we wanted the slope, but no more. We will not write m for the slope. What will we write? We'll write f prime. What we want is the slope at 1. Well, this is the f prime graph, so f prime of 1 just means go over here to 1, find that y value, right? That's what we've been saying all day here. The y values on f prime are the slopes of f. So this y value right here, 2, is the slope we're looking for. So there's our point and our slope right there. So from here on out, when we're doing equation of a tangent line, we need a point and a slope. That's what we're looking for. Not m anymore. f1 is the point, f prime of 1 is the slope. We plug that in and we don't even have to do anything with it. We're done. There's your answer to 47. Okay, we get the slope by reading off of the graph. All right, and the last one I think I had envisioned talking about was 54. So with your calculators, now when I record and try to capture the class, sometimes this doesn't work real well. We'll see if we can make it happen here. So, seems to be working. Mark, have you been the presenter? Yeah. Now you have been. You are the man. All right, so everybody go ahead and get your calculators out because I'm going to show you on this one where I would expect you to use your calculator and not. So go ahead and everybody, let's go into your graph screen here. And let's go ahead and delete that out of there. And let's put in that h graph. It was negative 16 x squared plus 38x, oops, what's happening here? I don't know. What are you doing? Plus, what? Okay, hit the plus sign. There you go. 38x plus 74. Okay, now we're going to have to set our window here. Go ahead and hit enter. Okay, now, we got a problem because it's way up there at plus 74, right? So let's go to our window. Now I'm going to show you a little trick here, a little zoom thing that is pretty nice. Go to your, go to your window settings, and let's set our window from -5 to 5. I think that's enough. And then that's it. Don't mess with the y. Just set your x min and max, -5 to 5. Hit OK. Just hit enter. Enter will do it for you. And then let's go back to your menu. And let's go to zoom. And we're going to do fit, which is down there, letter A. Zoom fit. And what that does is it looks at your x min and max, and then it sets the y's for you automatically, which is kind of nice. So if you know an X boundary you can use, this works pretty good. Okay, so here is the ball. So we're throwing this ball starting at a height of 74, 38 feet per second, initial velocity. It's going to go up, and then it's going to come down. This part of the graph we probably don't need to use. Probably shouldn't even have done the -5 because I really don't need those negatives. Okay, now go into your graph screen. Go hit tab. Hit tab's a quick way to get back to there. There you go. And let's put in the velocity equation. Let's put in -32x plus 38. Okay, and hit enter. And that is our velocity graph. Now that's also our derivative graph, right? Everybody right with that? It's h prime. So what we have, the red graph is h prime. The blue graph is our h. Okay, now hit the scratch pad key. And we're going to go on the calculator screen. Okay, so now let's talk our way through this. So A said, how high was the ball thrown from? 74. We know that's what this number means. Okay, part B. Part B says, what was the initial velocity? 38, because we know what that 38 is, feet per second. Was it thrown up or down? Up. How do we know? Because it's positive. 38 positive means it was thrown up. Okay, C. What's C say? At time 2, is the ball's height increasing or decreasing? How do we get this? Okay, now you've got two choices. Now there really isn't a lot of calculus here other than velocity we've now learned is also called a derivative, but really we didn't even need that to answer these questions. Go back to your graph, Mark. I know I told you to go here, but go back to the graph. Okay, so if you traced at 2 right now, so one way to be would be look at the graph. Now that's never a good enough answer on a quiz to say, well, I looked at the graph. So what you'd want to say is at 2, the H graph is decreasing. That's what you'd want to say. So if you trace at 2, Mark, go ahead and do that. Are you doing it? Oh, okay. The other class they were doing it, and then my computer froze up. That's why I asked. Type in a 2, hit enter, and sure enough, oh, okay. Not sure what that's doing, but it's going down. Okay. So go ahead and hit escape. That's fine. And, all right. What would be another way to do that, though? Let's imagine we did not have our graphing calculators with us. Plug it into what formula? That's right. So, V, and let's use our calculus notation. Here would be a great way to show this. You put in a 2 into the H prime, which remember, this is H prime right here, and you get -26. That alone tells you the ball is going down. The velocity is negative. Okay, so that would be probably a better way than using the H graph. All right, what does part D say? When's it hit its highest? Now, back to your graph. Okay, go ahead and hit trace. I see we've got a point there already. Go ahead and hit trace. Graph trace. Arrow, just hit your left arrow and get towards the peak. Now your calculator does kind of a cool thing. See that right there? Stop right there. Okay, the calculator will find automatically these maximums and minimums for you. Now I expected some of you to maybe use that on the, or I thought you may, if you thought about it on the test, on the quiz where we had that one about how many phone calls, when the most phone calls were made. Okay, but some of you did, and I think we didn't talk about it, so you didn't have to. But actually doing this is never good enough in calculus if you need to find a maximum. We have to show a calculus justification. We get to say I traced and that's the maximum. So it happens right here at 1.1875. What is true about the ball when it hits its maximum? The velocity is 0. So a great way to do this is to say, I'm going to find when the velocity is 0. So I'm going to solve this equation. Now this is such an easy equation, we can just do it without the calculator. It'll be -38 divided by -32, and sure enough, Mark, go and divide that, go to the calculator screen, and I'll bet we get 1.1875. Okay, well there it is right there. Take 38 divided by 32 and just hit Control Enter so we get a decimal. And sure enough, there's that number. So that's even a better way to do it. The last one says, when did the ball hit the ground? Or how long was it in the air? Which means, when did it hit the ground? What do you do to solve that? And don't use your graph. Put in 0 right there. Now, here would be a great way to show this on a calculus test. You would say, I'm going to solve that right there. I'm going to solve when h is 0. Now, you can do this on your calculator screen. This could have helped you maybe on number 20 as well. But so Mark, I want you to do this here. So let's go menu, algebra, solve. Put in the equation, negative 16x squared plus 38x plus 74 equals 0, comma x. Comma's down, there you go. Hit enter. You get a big messy thing like that because it would need a quadratic formula. Hit control enter. And there you go. The negative one we would throw out because that was before we threw the ball. And there it is, 3.644. That's how long the ball was in the air because that's when the height was 0. So there really was no calculus there, just solving some algebra equations and plugging some numbers into these functions. So the only calculus involved in that problem at all was the fact that velocity is a derivative, and we've talked about that so notationally, but there was really nothing else there. So that's just using those formulas. Okay? All right. Thank you, Mark, for doing it. All right. So now, let's talk briefly about section 1.5, and then I'll let you have some work time here. So if you turn in your books to page 47. Now, well, here I let Mark off the hook, and now we do need the calculators again. All right. So when you get your notes out, we'll probably jot down a few things here. Courtney. I honestly, you saw me. I did not know. I picked it random. But look at that. She's got it all right there. Everything's working good today. All right. So, this section is, there's not a lot in this one, okay? This section is about, as it says, estimating derivatives, taking a closer look. So that problem we did yesterday where we zoomed in until the line was straight. That's what we're talking about today. We're going to zoom in until the line is straight, and we're going to talk about finding this slope. So one way we have of finding slope on a curve is we sketch in a little tangent line and we do our rise over run. Okay, that's one way. But we can do better than that if we know an equation we want to work with. So let's take, in your book, they've got this graph, y equals x squared. So Courtney, go ahead and take out those graphs you had before, and everybody should probably do this. Go in and let's graph y equals x squared. Okay, and we're going to look right here at the point 1, 1 on that particular graph. Okay, and I'm going to draw something here. Draw myself a tangent line. Okay, it's kind of what we're looking at. But if we go onto our calculator, and let's delete that out of there. And, okay, arrow up. There you go, delete that one. And arrow up. Oops, deleted the equals. That's okay, go to 3, arrow up there. There you go, arrow up one more time. There you go, delete that one. All right, and let's put in just x squared. Put in x squared, and let's go to our window. And let's go, negative 5 to 5 is fine. Go to your window settings. So negative 5 to 5 is good. And for the y, let's go like negative 1 to 4. For the y, let's go negative 1 to 4. So this would be the picture that we're looking at on page 47. Why is there not a picture there? Hit tab, arrow up. Oh, it's unchecked. Yeah. Just move your finger on your trackpad. I'm not sure of a good, yeah, there you go. And then click. There you go. All right. Now, and then hit escape and that, or tab, and that'll go away. That's, maybe. Does tab, maybe tab doesn't make it go away. There it is. Okay. All right. Now let's trace at 1. Now a little bit of a trick, if you want a point to stay on a graph while you work with it, you can hit enter twice here. So if we go to graph trace and type in a 1 and hit enter, now hit enter again, and it'll actually stick that point there, and that point will stay on our graph then. Okay, and what we're going to do here is we're going to zoom in like that problem we did yesterday. So go ahead to your menu and zoom in. Courtney, you're doing such a good job, we might just have you do this every day. All right, and so then move your little magnifying glass to over the point, yeah. Yeah, on top of the point, yeah, on top of 1, 1. There you go, and then hit enter. Okay, and then again. Okay, and one more time. Okay, that's pretty good. All right. Oh, Jesus, going all over the place. What's going on? Okay, that's good enough. All right, now. So now we've zoomed in until this thing is straight. Okay, until this thing is straight. Now, let's have everybody, let's try this. We didn't try this in the other class. I want to try this for our homework. So let's go to menu and window trace and trace step. Go down to trace step, number 3. And let's change this from automatic. So hit your right arrow, put enter a value, and let's go 0.00, let's put 3 zeros, 0.0001, and hit OK. Now later we'll go ahead and change this back, but just for this homework I want to do that. All right, so now, all right, 3 zeros, so 0.0001. All right, now here's what we're doing. Here's the concept I want you to get. What we have done is we have just zoomed in so that we on our screen are only looking at this little piece of the parabola, right? So when you're in that little tiny piece, how much difference is there between the tangent line and the curve? Not much, hardly any. That's the idea of local linearity. When you draw a tangent, because remember, now let's be real clear about this. This is really a key point. When we do the slope of a curve, we're really doing the slope of the tangent line. To do the slope with 2 points, we need 2 points on that line. Do we know 2 points on that line? We only know this 1 point that's on the line and the curve. So now, back to Courtney's picture, back to your graph, if she now goes to trace, so everybody can do this, go to trace, and trace, graph trace, and type in a 1, hit enter. So we're now on this point. Now hit your right arrow, Courtney. Hit your right arrow. Did everybody see that? Did it move just a little tiny bit? Okay, it moved just a tiny, tiny bit. Now, is that new point on the tangent line or is it on the curve? It's on the curve. So if I was to do a slope right now, remember here's this point right here. So if I was to do this slope, really slow with the Wi-Fi and the video taking. Okay, if I was to do this slope right here, because remember my original point was 1, 1, right? So if I was to do this slope calculation, would that be the slope of the line? No, because this second point is not on the line. But it's really, really close to being on the line. It's on the curve, but when I look at this, when I look at this teeny little piece right in here where I've zoomed in, the tangent line and the curve are essentially the same thing. But when I trace along that curve, I am not on the line. The 0.11 is on the line, but none of those other points are. But I zoomed in to where it looks straight, which means that part of the curve is basically like the line. All right, so you're going to be doing some of this on your homework today. You're going to be doing slope calculations like this, where you're going to trace to a point. So if they ask you, find f prime at 1, estimate f prime at 1. One way we have of doing it is sketching a tangent line and doing a rise over run slope triangle. Another way we have of doing it is tracing it. If we have an equation, we can graph it, we can trace it, and we can move like 1 point away, and we can do that slope calculation. So take the point that they want, which was a 1, move 1 or 2 or 3 clicks away to get a second point, do a slope calculation. I want you to write this on your paper. I want to see this on your paper, and then calculate that out. Okay, now is that going to be the exact slope at 1? No, but it'll be really close. It's going to be really close. And if we wanted to get more accurate, what would we do? Put more zeros in there, right? Get closer. Let the 2 points get closer. Okay, so that's the main idea behind this lesson here, is this idea of zooming in. And now we already talked about that door and the degrees, and we already talked about 2 points getting close, so that's why this section is going to go pretty quick, because we've already kind of talked about these ideas. Okay, turn to page 49. I want to mention 2 other quick things, and then Courtney, you're going to get to draw one more graph, so go ahead and delete that graph off there. But on page 49, there is a V graph, and we already talked about this. That sharp point, what's the derivative there? Undefined. Undefined. So there are 2 times when the slope, when f prime is undefined. If you want to jot this in your notes, maybe. I'll leave this up here. There are 2 times when f prime is undefined. One is at a sharp point on a graph. Now that can happen a lot of different ways. Sometimes we get graphs that go like this and then take off. They could be curved, and they come in, and then they have a sharp point. That's one time when f prime is undefined, when you have a sharp point. The other time is when you get a vertical tangent. Here's a graph. This is x to the 1/3, cube root. Right there, we've got a vertical tangent. Vertical lines, of course, are undefined also. So those are 2 places when the derivative is undefined, at a sharp point or when you get a vertical tangent line. Okay? All right. So there might be a little bit about that. And then finally, the last thing on page 51, and I'll put this back up here in a second if you didn't get that jotted down, but let's go onto our graph screen, and let's graph y equals e to the x real quick. So let's graph e to the x. Oop, different e, not that e. This e right here. Oops, where'd that come from? Not that e. Yeah, there's a lot of e's on this keyboard. This e right here. That's so I didn't even. There you go. E to the x. Okay, hit enter. She just screwed that up because she wanted to get fired and not have to do this all the time. All right, and now let's go to your window. Go to menu, window, and let's do 5, zoom standard. Number 5, zoom standard. Okay, here's e to the x. Now, I want to show you something really cool about e to the x. One of the things people always ask is, what's special about 2.714? Why is this e so special? What do we mess with for? Here's one reason. Go ahead and trace at 2. Okay, and hit enter again. Okay, so there's the e, that's e to the second, is that number right there. Okay, now I also want you to go on under menu and go to analyze graph. And this line right here, it's not something we hardly ever use, But number 6, dy dx is another name for derivative. So go to number 6 for derivative. And position, they want to know which graph we're talking about, or where we're talking about. So go ahead and move the little hand, the little pointer right on top of that dot right there. There you go. Hit enter. It didn't work. Click right on that. Okay, now click on that point. Or maybe we hit tab. Oh, come on. Why is this not working? Oh, wait, we're out of it. I'm sorry, we did it right here. Go back to menu. Go back to menu. Go back to menu. Go back to analyze graph. dy dx. Okay, now point. Okay, hit enter. Okay, oh shoot, now it's kind of in the way. All right, let me borrow. Yeah, now this is not the fault. Okay. All right, here we go. All right, so right there. All right, move that arrow off there, would you? What we just did is we found the slope at this point. It's this right here. What do you notice? It's the same as the y value at the point. E to the x is the only function where that is true. Every point along here, the y value is the same as the slope at that point. Only function that has that property. So it's just one of the special properties that E has. So you just learned your very first derivative formula right there. E, if f of x is e to the x, then f prime of x is also e to the x. It's its own derivative because the y values are supposed to be the slopes. Well, for e to the x, its y values are its slopes. Okay? Only function has that property. Okay, your homework is section 1.5. You can have the last 20 minutes here to work on that. Now, there is a second assignment that is not due till Monday, but since this assignment's a little shorter, if you want to start, it's probably a little shorter than the one I give you tomorrow. So if you want to get started on that, that's not a bad idea. It's a little reaction article I want you to write. I want you to read an article, I want you to react to it. Now, the title of the article, this is on Classroom. Is mathematics necessary? So here's the article right here. You open that up and read it. Write a short, now I said 1 to 2 page. Now, I don't mean it could be 2 paragraphs, right? It could be half a page. You could write a lot in a half a page probably. Okay, but I don't want you to say, oh, it's great. I liked it. I agreed with it. 2 sentences. I don't want that. But some people get so excited about the article, they might write more than a page. That's the only reason I put that. Okay? Do you agree with the author? Do you disagree? What do you find interesting about the article? And then I want you to create your Google Doc right in here on Classroom. So when you go to Classroom, you click on this assignment. It'll open up an option for you to create a document. You create it right there. It'll name it, do all that for you. You type it, and you turn it in right from within Classroom. So I want everybody to do it on this. And that is due Monday at the start of class. Okay? So I don't care, you want to work it tonight or whatever, but that's due Monday, start of class. So section 1.5 and this reaction. Okay? All right. The rest of the time is yours.